Everybody, welcome to today's talk, which is about Introduction to Recursion. The topical guide objectives for today are 1. Understand recursion and its application in problem solving. 2. Identify base cases and recursive cases. And 3. Know by heart specific examples of recursive code. 1. Fibonacci, 2. Sum of first n numbers, and 3. Factorial. So we'll go over some of these in today's class, and then we will continue on next time. So let's take a moment to review subroutines. We've talked about subroutines in the context of writing functions that call other functions. For example, you could have a main where you create A, you create B, and then you say, let's say C is equal to add of A comma B. That's going to call elsewhere, right? So it's going to go find the add function, add of xy, total is equal to x plus y, and return total. So now C is assigned to whatever that value of total is, and we can output C. So this is review of when we started talking about functions for the first time, and we wrote these little routines for that. So the big takeaway here is the fact that you have this arrow that calls elsewhere. So basically, when you reach C, our program calls to some other memory location. So functions can call other functions. For example, main calls the add function. So main points out to add, and then it does add, and it'll go back and return the output of C, as we saw previously. Now, a recursive function, on the other hand, calls itself. So now I have some compute that just goes through and just calls itself directly. In other words, the word compute appears within the function called compute. So this doesn't really make any sense the way I'm doing this, because it seems like we're going to get stuck in an infinite loop. But there is a reason to do this, and it has to do with how we call compute. So per topical guide objective 1, we want to know what recursion is. Recursion is a programming technique where the solution depends on solutions to smaller versions of the same problem. So let's look at an example of a recursive function calling itself. Let's say we have def compute x. If x is equal to 0, return 1. Okay, that's what we have so far, and the word compute has not appeared within compute yet. So here, else y is equal to 2 times compute of x minus 1, return y plus 1. So right here, where y is computed, it actually calls compute again. All right, so this is generally going to be the breakdown of a recursive function, where you have an if statement that doesn't call itself, call the function itself, and an else statement where it does call the function. Okay, so the main purpose right here is to see that there is a structure with 2 parts, which is the base case and recursive case. Let me define what those are. Cases in reduction are, as I just said, the base case, which means that if the problem is small enough, we can go ahead and solve it directly. A recursive case, on the other hand, is something that divides the problem into one or more simpler instances of the same problem, solves it recursively, and combines the solution. If you find it confusing to call the recursive case itself, you can think about it as somebody solving the smaller problem for you. For example, this recursion fairy can do it. Okay, I think we can go ahead, and now that we have the definition of base case and recursive case, we can look at that example again. So, recursive functions call themselves. We first have this if x equals 0, then return 1, else y is equal to 2 times compute x minus 1, return y plus 1. Now, if x is small enough, right, if x is 0, there's no reason to call a smaller version of x. And so you just say, let's go ahead and return. I'm done. It's just going to be the base case. On larger values of x, though, we can't compute it directly, and this is where we're going to need the recursive case. And so that's why we have y is equal to 2 times compute of x minus 1. This also showcases how we are going to need to do some sort of combination. So y is equal to 2 times compute of x minus 1. So there's some other mathematical stuff going on here. We also return y plus 1. Now, as I just mentioned, if it's confusing to think about this recursive case as if you don't want to like put the function inside itself, you can think about it as having someone that's going to solve simpler versions of the problem for you. So again, looking at the recursive case right here, that's where you would say, look, I've simplified this problem. It's slightly smaller now, and you can do this little piece for me and return it to me. And once you are done, I can combine it in a particular way. Good. So this is a particular example that showcases the general structure of a recursive function. And as I've mentioned before, we want to know a couple of particular recursive functions by heart. So let's look at a slightly more complicated example, which is the Fibonacci sequence. I'm just going to read out the function for you. Def f of n, and then two if statements. If n is equal to 0, return 0. If n is equal to 1, return 1. Else, return f of n minus 1 plus f of n minus 2. So we have, again, a recursive case, but you'll notice that it's adding two things together, where the smaller cases are n minus 1 and n minus 2. So in this case, we actually have to have multiple base cases, and we are going to combine them together in the recursive case. And you can think about this as having two different helpers that will magically solve the previous cases for you before you are ready to combine them. Good. So this Fibonacci sequence is one of the ones that you should just know by heart. So it's covered under Topical Guide Objectives 3.1. Let's take a look at it a little bit more to make sure we really got the point. The recursive case does need to call on a simpler input. So it's really important here that it's n minus 1 and n minus 2. It's getting smaller every single time. And there is going to be a requirement that n is greater than at least greater than or equal to 0. Otherwise, this would go on forever. So that's one more thing to keep in mind. So another example of recursive code is the use of the factorial. Take a moment to remember how to define factorial and maybe try calculating out 4 factorial. Okay, so the way factorial works is it's a multiplication of all the numbers of that number down to 1. So 4 factorial is 4 times 3 times 2 times 1, which is 24. So this is kind of an iterative definition where I just wrote it all out ahead of time. But if I knew what something factorial was already, I could just multiply the next number. Let me show you what I mean by that. N factorial, in general, can be written as 1 if n is equal to 0, and n minus 1 factorial times n if n is greater than 0. Right? So here we have a base case, which is what happens when n is equal to 0, and a recursive case, which takes in a smaller instance, n minus 1 factorial, and continues. Okay? So let's look at another example to get this a little bit clearer in our heads. And I'm not going to make you answer this because it's quite large, but what is 9 factorial? The answer is 362,880. Now, if you wanted to calculate 10 factorial, how would you do it? All right, let's take a look. We already know what 9 factorial is. I mean, somewhere the recursion fairy calculated out 9 factorial for you. And so I know that 10 factorial is literally 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, or more simply put, 10 times 9 factorial. And so here, if I already know what 9 factorial is, it's super easy for me to calculate 10 factorial. In other words, n factorial is equal to n times n minus 1 factorial, or, you can flip it around. That is exactly that recursive definition that we had. So this is the recursive case right here. All right, now what I want you to do, and you can pause this video, is take a moment to try to take the factorial definition that we have and write it as recursive code using the base case and recursive case that we have defined. So I will wait about 2 minutes or I think it should take you about 2 minutes to do it, but I recommend you pause the video and then I'll continue. Great. So let's go ahead and move on to looking at factorial code in Python. I'm going to give you a wrong answer. Right? So here I have def fact n is equal to n times fact n minus 1. Now this is problematic. You can pause the video and think about why it's problematic, and then I'll run through an example. Right, so let's look at an example of fact of 3. Okay, so 3 factorial, that should be 3 times 2 times 1, or 6. So I'll run it through. 3 times fact of 2. Okay, fact of 2 is 3 times 2 times fact of 1. Continuing on, 3 times 2 times 1 times fact of 0. And now we're going to go on. 3 times 2 times 1 times 0 times fact of negative 1. And we're going to go forever. So what needs to be added to this code to fix it? Great. So now I've made some changes to my factorial code. I have def fact of n, and if n is equal to 0, I'll return 1, else I'll return n times fact n minus 1. So what I was missing previously was that base case. I had the recursive case, but I did not have the base case. And if you forget the base case, it's going to turn out that your code is going to run over and over and over again and until your computer just basically stops working. So you need to always make sure, as per Topical Guide Objective 2, to have a base case and to have a recursive case. The last example that I want you to be able to do by heart is sum of first n numbers. But for this one, I'm just going to have you give it a try, and next time we will start with a review of what the sum of the first n numbers is. And the other thing that we'll do next time is talk about stacks. So that's all I have for today. Does anyone have any questions or comments?